back with another TDengine video, and today we're going to be talking about the core data modeling within TDengine. TDengine's real power comes from your model data, and in this video we'll break down how the building blocks work, databases, supertables, subtables, tags, and metrics, and how they cover your best practices so your schema stays fast, scalable, and maintainable. So let's talk about the core data hierarchy. It starts with databases. A database is a TDengine logical container. It controls the retention policies, replication, and overall storage behavior. You can usually create a database based on your environment or workload. Supertables are another kind of data hierarchy. It's a template. It defines a structure for the class of devices or signals that all share the same metrics. And then you have subtables. Subtables represent a single producing entity of data, one inverter, one motor, or one machine. Each subtable inherits schema from the supertable, hence it's a template. So let's start with a database. A database is that top-level logical container, and it establishes different boundaries and overall storage behavior. Each database defines the critical operational parameters that also uniformly apply to contained structures. You could think of it as keeping retention, replication, and storage. You usually create a database based on the environment or workload, production versus test, or the kind of data, not based on the kind of device. Okay, what about supertables? Well, supertables define a schema template. And within that schema template, supertables are a structure of classes for devices. This is where you get what's measured over time. You do not directly store data in the supertables. You store data in the subtables that inherit from this supertable. So think of it like the map that the subtables follow. Cool. So what are subtables? And this is where TDengine's one device, one table philosophy is core to the architecture. Each subtable represents a single device, sensor, or source. This one table per device architecture is fundamental to TDengine's performance model, enabling lock-free parallel writing at scale. So that is what's key to TDengine's performance. And for example, we have a couple examples here, like a solar inverter would be a subtable, or a single electric motor would be a subtable, and a process sensor would be a single subtable, or a CNC machine would be a single subtable. Okay, moving on. What are metrics? Metrics are time-varying measurements. These can be anything, temperature, pressure, voltage, power, speed, whatever you name. As long as they change over time, they're metrics. They're time-stamped, and if it changes frequently and you want it to trend, it's a metric. So it's an easy way to think about it, and they're stored efficiently in chronological order. So what are tags? Tags are static. Unlike metrics, they never change. Things like location, model number, site number, asset ID, manufacturer, or capacity class. Tags do not change every second. They describe the device, not the measurement. So here we have a couple examples: the site location, the asset ID, the model and make, and the capacity ranking. So why does this separation matter? This separation allows TDengine to scale. Tags are indexed and optimized for filtering and grouping across thousands of millions of devices, and metrics are for time. Tags are for identity and context. So you can think of metrics as time-based and tags as identity-based. Cool. So how does TDengine actually use this one table per device model? Well, TDengine's performance advantage comes down to it, right? Each device writes to its own subtable, and this allows for lock-free writing because of the extremely high ingestion rate, because devices don't contend with each other for the same table. Unlike a traditional database where many devices write in one large table, TDengine isolate writes at the subtable level. This leads to parallel ingestion, linear scalability, and lock-free writes. So the effective TDengine modeling thinks differently than relational databases. Designed by signal types, the stabilization of tags, the avoidance of overnormalization are all things that are beneficial and requires different thinking than relational databases. Some mistakes that people often make are using one super table for device, or rapidly changing tags, or relational thinking. All of these will negate those performance improvements that I just talked about. And there you have it. Based on what I've just told you, if you understand the databases, supertables, subtables, tags, and metrics, and you understand TDengine's core, you'll be able to create changes that are meaningful from traditional databases and be able to ingest and query data at a much higher rate. And because of this, TDengine is world class in its performance and its design. Thank you.